So we have already seen the reaction of carbene, singlet carbene and triplet carbene generated on direct photolysis as well as on sensitized photolysis. Singlet carbene generated on via direct photolysis is deuteronic in nature, whereas triplet carbene, which is generated in sensitized under sensitized condition, is diradical in nature. And the reaction of this we all so today also again we'll see few more examples on uh, few more examples of reaction of singlet and triplet carbene. So we already seen the let us say when we have a CH2N2 diazomethane on photolysis direct generates carbene singlet carbene is a zootronic in nature. Zootronic mode of reactivity. Zootronic mode of reaction. On the other hand, irradiation in sensitized condition generate CH2 and the triplet carbene, and this is radical mode of reaction. So it has been found that when this the carbene generated the singlet carbene reacts with methanol, reacts with toluene. So I will just so singlet carbene reacts with toluene into a different mode, like the CH2 singlet mode of reaction with methanol, mode reaction of singlet and triplet with toluene. Right? This singlet carbene reacts with the toluene plus, so we can write toluene like this, H. So this and then it gives rise to a CH3 CH2 pH. It gives ethyl benzene as product. Is a concerted concerted insertion. Ethyl benzene and formed through concerted insertion. No, and it has been found that it doesn't give CIDNP. No CIDNP. This is a NMR technique which determines the reaction. NMR technique. NMR determines the reactions reactions involving radicals. So here the no CIDNP was observed because no radical species is involved, and the reaction is proceeding via concerted insertion of the insertion of singlet carbene to toluene to give ethyl benzene. On the other hand, if we have a triplet, so this is generated from CH2N2 on direct photolysis. If we do reaction in the presence of benzophenone as a sensitizer, it gives CH2 a triplet carbene. The radical mode of reaction, triplet carbene, we have already seen this, and this adds with same toluene, CH2 H abstract and hydrogen atom to give CH3 radical plus benzyl radical, CH2 radical, and then this can combine to give CH3 CH2 pH. Ethyl benzene product is same. This is also ethyl benzene, but this observes the radical addition. This involves radical addition and it gives CIDNP. It CIDNP, because this gives CIDNP indicates that the reaction of triplet oxygen with the toluene giving rise to ethyl benzene is proceeding via radical addition. There is another example. We get different products from the same reaction, which indicate that the reaction, the singlet example, where singlet and triplet carbene gives different products, indicating different mode of reactivity, different mode of reactivity. So here what has been found that the irradiation of diazoacetophenone is an example of irradiation of diazoacetophenone in alcohol. Gives two different products. So if we have a pH, CO, CHN2, this is diazoacetophenone. On photolysis, loses nitrogen, generate pH, CO, CH, singlet carbene, whereas this, in the presence of sensitized photolysis, generates containing isopropanol R2CHOH as the sensitizer, generates PHCOCH triplet carbene. And this in the this singlet carbene gives the product obtained is rearranged product PHCH2 CO2CH3 is an ester rearranged product. Rearranged product is formed when the carbene is generated, singlet carbene is generated on direct photolysis. On the other hand, the triplet carbene, which is generated on sensitized photolysis, gives different product, that is PHCOCH3. This is acetophenone. Is a triplet product. Singlet product and the singlet carbene product is a triplet. So you can see two different products are obtained via different mode of reactivity with the singlet and triplet. The reaction can be well understood via the mechanism. So if we have a mechanism involves like this, we have the diazoacetophenone PHCOCHN2. So diazoacetophenone on direct photolysis gives C double bond O PH CH. This is singlet carbene. This is singlet ketocarbene. So the reacts undergoes 1-2 shift. 1-2 shift. 1-2 shift to give ketene as a C double bond O double bond C as C double bond O on CH PH. So let's write in double PH CH double bond C double bond O. So this is ketene, which in the presence of methanol gives PHCH2 C double bond O OCH3. This is the ester. On the other hand, this on photolysis, on sensitized photolysis, minus N2. Sensitized photolysis minus N2 give PHCOCH. This is the this triplet carbene. And this triplet ketocarbene reacts with abstract hydrogen atom from R2CHOH, hydrogen atom abstraction, gives rise to PHCH2 and then plus CH2COPH, CH2 radical plus R2 plus R2COH radical pair, and then this gives rise to acetophenone, and then of course this ketone PH C double bond this is CH PH CO CH3. Ketone is the and plus of course here also we get the same R2CO. R2CO. So you can see this is really a very interesting reaction which very clearly demonstrate the different mode of reaction of singlet carbene which goes via rearrangement 1,2 shift to give ketene, which on reaction with methanol gives ester as one of the product. On the other hand, triplet carbene reacts abstract hydrogen atom, involves hydrogen atom abstraction to give this radical pair, which in turn gives rise to this as the one product. So we see the different mode of reactivity of the singlet and triplet carbene. So now we just look into few the reaction of photo-induced electron transfer reactions. Few examples of photo-induced electron transfer reaction. We have already in the introduction we have mentioned that the photolysis can be brought about by two different ways: direct photolysis or through indirect photolysis. Indirect photolysis, we use a sensitizer which can either transfer an electron or it can transfer an electron. When it transfer electron, it's called photo-induced electron transfer. These again of two types. So now today we would like to see a few examples of homogeneous photo-induced electron transfer reaction. Photo-induced electron transfer. In this one, both donor, we have a donor and we have an acceptor. In the presence of light, donor gives an electron, acceptor accepts an electron. We have a donor which gives an electron, donor radical cation and plus acceptor radical anion. This is taking place in the presence of light. The most important donor and several examples of these acceptors are DCN, dicyano 1,4-dicyanobenzene, CN 1,2-dicyano, and DCA 1,2-dicyanonaphthalene, 1,2-dicyanobenzene. So we have all three: dicyanobenzen, dicyanonaphthalene, dicyanoanthracene. These acceptors have been used extensively as a. So we have a. This is dicyano. It's a very good electron acceptor, and the donors are this is 1,4-dicyanonaphthalene, 1,4-dicyanonaphthalene, and this is 9,10-dicyano. So this is 9,10-dicyanoanthracene, 9,10-dicyanoanthracene, 1,4-dicyano, 1, 2, 3, 4. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9,10-dicyanoanthracene, 1,4-dicyanoanthracene. This is 1,4-dicyanobenzene. These are very good substances. Whereas donors are electron rich alkenes act as a very good donor. Electron rich alkene acts as a good donor, and we generate. So what happens when we have a system like this? Say we have an alkene acts as a donor. We have a dicyano-benzene is an electron acceptor. So we generate radical cation plus dicyano-benzene as radical anion. So this type of the trapping of these radical cation and is form the donor with the trapping examples, or several examples are available. Several examples which involve the trapping of the radical cation species by a nucleophile. Examples available which involves trapping of radical cation by nucleophile. So we'll see a few examples of these trappings. So if we have a system like this, so you have this indene. Of course, this alkene acting as an electron donor, and then when it is irradiated in the presence of dicyanonaphthene, dicyanobenzene in methanol. So it gives radical cation, and then this radical cation is nicely trapped by methanol to give a one, two, three. So we have a methanol OCH3, a radical here, and this has been found to further use a copper second has been used as another reagent for electron transfer, copper 2, and then followed by and it further generates a cation. OCH3 and OCH3. So we can see here the reaction involves the electron transfer reaction under photolytic conditions. Is a homogeneous photoinduced electron transfer is a act as a donor, transfers electron to generate a radical cation. Methanol act as a nucleophile, traps this, and then the radical is further converted to a cation species, another is cation species, and then this reacts with in the presence of methanol, gives this product. So you can see the trapping OCH3. You can see the trapping of the by nucleophile has been observed of the radical cation species which is formed during the electron transfer reaction. Is another example which involves the trapping by nucleophile followed by the rearrangement, that is 1,2 shift. So if we have an alkene like this, pH, we have a cyclopropyl derivative, we have an R here, of course H here, in the presence of under photolytic condition, dicyanoanthracene is an electron acceptor, methanol is the solvent, and it generates, of course, generates a radical cation followed by abstraction by methanol, trapping of the cation by methanol, as we have seen in the previous slide. Here you have a phenyl group, and then in the presence of the copper 2, it generates a cation through electron transfer reaction, OCH3 R. This is converted to cation. Now there is a shift. There is a shift of the 1,2 shift of the cyclopropyl group. 1,2 shift of the cyclopropyl group to get a carbocation here, OCH3 R. We have a cyclopropyl, which is phenyl group here, this H here, and then this in the presence of methanol can lead to OCH3 R, cyclopropyl group, phenyl group as H. Now, 2-methoxy group, the same carbon is unstable, and then this is converted to corresponding ketone. C double bond O R, pH, H. So you can see a very nice rearrangement of this alkene through photoinduced electron transfer reaction using dicyanoanthracene as an electron acceptor. This gives undergoes under photolytic condition photoinduced electron transfer to generate a radical cation. Radical cation is quenched by methanol acting as a nucleophile. Cyclopropyl shift followed by once again attack of the methanol as a nucleophilic fashion to give a dimethoxy substituted, being unstable, converted to keto derivatives. So this is another interesting example of we see another example here of a similar type, trapping of dimeric trapping of dimeric cation. So if we have an alkene like this, CH2 pH CH3, this in the presence of light, dicyanobenzene as an electron acceptor generates C double bond CH2 radical cation, pH CH3, and then this reacts with, this is the donor, reacts with another molecule of donor to give a cation. Here is a radical here, CH3 pH, and then we have a CH3 pH. This once again, this cation is trapped by methanol, CH3OH. OCH3 CH3 pH, and then we have a radical here, CH3 pH, and now this undergoes plus one more electron, become anion. This is the first step, and second step is the abstraction of a proton. So we get a product. First one electron is converting this to anion, and then it abstracts a proton to get H, CH3 pH, OCH3 CH3 and pH. So this we can see a very nice photoinduced hydrogenation or reduction of carbon-carbon double bond in the presence of dicyanobenzene and methanol being the solvent. Protic solvent gives the saturated dimeric adduct. Dimeric This is a dimeric adduct, methanol added. Dimeric radical cation. Reacting another molecule of D to give this dimer which abstracts the proton, and then so that's all for today. Thank you very much.